So let's keep moving with some acceleration practice here. So you need your calculator out, equation sheet out, all those things, okay? It says during a race, a sprinter increases from 5 meters per second to 7.5 meters per second over a period of 1.25 seconds. What's our average acceleration during that time? So we know that when we're solving for average acceleration, that's just acceleration, right? That's the equation that I gave you is for average acceleration. Let's go ahead and write out what we have. Let's go ahead and figure out what we do have. We've got our sprinter increases from 5 meters per second to 7.5 meters per second. So what does that mean? What do these values represent? Good. Initial and final velocity. So which is my initial velocity? 5. So VI is 5. V final, right? Velocity final is 7.5. And then our time is 1.25. How do I know those variables? How did I know automatically that this was velocity?
Meters per second.
Right, the units, right? The units tell us that that is velocity because that's what velocity is measured in, meters per second. So I have both of our velocities and I've got my time. It says I'm trying to solve for acceleration, so I'm going to give that my question mark, right? What is it that I'm solving for? And then I'm going to go from there, right? My equation for acceleration is the acceleration is equal to change in velocity over change in time. Now, I very rarely write this delta for time because we don't ever have a starting time and a final time. We just have a time, right? And so really our starting time is always 0. So there's no need for me to write initial and final for time. So you'll see me kind of just tend to write over t, okay? So let's go ahead and plug in what we have here. Remind me one more time, what does this delta, what's that mean? Change in. Or another way to say it is final minus initial. So when I go to plug in my acceleration, I will take my final velocity minus my initial velocity over my time. Okay, final minus initial over t. All right. And then I'll go ahead and plug that in. So that's 2.5 over 1.25. And so that gives me an acceleration equal to 2. Right? And what's my units for acceleration?
Meters per second squared.
Very good. Meters per second squared because it's essentially meters per second over seconds. And that's how we come up with that, meters per second squared. Very good. Tell me, what questions do we have about solving here? Are you able to pick out those variables from the equation? Initial velocity, final velocity, time, all that kind of stuff? Okay. Let's try another one here.
What if it is half like what is it?
All right. This one says Marissa's car is moving at a speed of negative 28.6. Sorry, that got slid to the next line. So it should be negative 28.6. She slows down to a speed of negative 24 meters per second during a period of 3.2 seconds. What is her acceleration? Okay, so let's think about this. What's my negative velocity tell us? What does negative velocity tell me? That we're going backward. We're going backward. Or south or west, right? She's driving. So that means she's probably going south or west. Because if I draw my coordinate system, north, east, south, and west, these are my positive directions, and these are my negative directions, right? So if we're moving south or west, that's going to give us negative. Okay? 28.6, negative 28.6, what variable does that represent? Velocity initial. Okay, right? It's our initial speed or our starting speed, negative 28.6. My negative 24 is going to be my final velocity. And my time is equal to 3.2 seconds. All right? And then I just plug it in, very similar to how we solved the last one. Right? Acceleration is equal to final minus initial over t. we need to be really careful here when we do final minus initial. Sometimes it's easy to just take the one that's listed first minus the one that's listed second. Right, but we really got to know which one's initial and which one's final so that it goes in correctly. What happens to the math here? What happens when I do this math? It ends up being negative 24 plus, right? I've got two minuses or two negatives or whatever next to each other. They're going to become a plus. So that means I'm going to take negative 24 plus 28.6. Then I need to divide that by 3.2, and I get an acceleration equal to about 1.44 meters per second squared. Okay, my acceleration came out positive here. Does that follow the rule that we gave? Does that follow the rule we gave for on acceleration and the sign?
Yes.
Yeah, because it says if it's slowing down, the sign of the acceleration and the sign of the velocity are opposites. So in this case, we were slowing down, right? She was moving 28.6 meters per second, and she slowed down to 24. And those were in the negative direction, so that means our acceleration should be positive, which it is. Okay, does that part make sense? You feel good? Okay. We need to remember a couple things about velocity and acceleration. They are not the same thing. Velocity and acceleration do not mean the same thing. Velocity is telling us how fast our position is changing, the rate at which our position is changing, and acceleration tells us the rate at which our velocity is changing. So if our acceleration is 2 meters per second squared, that means every second that goes by, our velocity gets faster by 2 meters per second. Okay, so let's say that I'm moving 10 meters per second and I'm an acceleration of 2. That means after every if a second goes by, now I'm moving 12. If another second goes by, now I'm moving 14. If another second goes by, now I'm moving 16. So I am moving faster and faster and faster with every second that goes by. Does that make sense? Okay. Let's try this one. It says a car that's moving 75 kilometers per hour comes to a stop in 5 seconds. What is my acceleration? Okay, do we see any kind of red flags here? Okay, that is part of the problem. It's not an issue for us, but it is part of the problem we've got to think about. What else do we see that maybe is a red flag?
Hours and seconds.
Yeah, we've got units that are not consistent. Okay, here our velocity is measured in kilometers per hour, but our time is measured in seconds. So we usually want our acceleration to be in meters per second squared. That's going to be the general unit we need for acceleration. And so which of these do I need to convert? Do I need to convert my velocity or my time? I need to convert my velocity. Do you remember the shortcut to convert kilometers per hour to meters per second? Good. Yep, good. Kilometers per hour, to convert it, I need to divide by 3.6. Okay? 3.6 is my division to get me from kilometers per hour to meters per second. Remember, if you don't remember that conversion, here's what it looks like. If you weren't sure about the shortcut, I would go 75 kilometers per hour, right? I'd say 1 kilometer equals 1,000 meters, and 1 hour equals 3,600 seconds. So I'm doing the same math there, okay? But 75 divided by 3.6 gives me 20.83 meters per second. I've got my velocity. Is this going to be my initial velocity or my final velocity? This is my initial velocity, is 20.83. What do I know about my final velocity? Or do I know my final velocity? It's 0. Why is it 0? It's coming to a stop. It's coming to a stop, right? It is coming to a stop. If the problem had said it started from rest, what would our initial velocity be? 0, right? So we got to make sure that we're reading context clues in the problem. It says our time is 5 seconds. So now I'm going to set up my acceleration problem. Acceleration equals, am I going to do 20.83 minus 0? No, my final velocity is 0. Minus 20.83 over time. All right, and so that gives me an acceleration equal to about negative 4.17 meters per second squared. I want you guys to practice plugging these into your calculator. I don't want you to just watch me do it and assume you can, right? I want you to make sure that you know we have to do this, then hit enter before we divide by 5. Because if we don't, we're going to have problems with order of operation. So make sure that you are in your calculator doing your numerator, hitting enter, and then doing your divide by 5, okay? We're gonna start adding to our realm of equations here. I'm gonna give you a few more equations, but with either by yourself or with someone around you, I want you to try to answer this question. If the acceleration of an object is 0, does that mean that my velocity is also 0? No, that is not the case. What's an example of that? Bingo, right? If I'm at constant velocity, that means my acceleration is 0, but I'm still moving, okay? So this would be like if I have the cruise control set or whatever it might be, but if I have constant velocity, that means that I still have velocity, I'm still moving, but my acceleration might be equal to 0, okay? All right, very good. We are going to start looking at a new set of equations called the kinematic equations. Kinematic equations for constant acceleration, okay? Or I'm going to call them your kinematics, okay? There are 3 big equations that we get in this kinematic section, and they allow us to really study how things move, right? How fast, how far, how long. Those are the types of questions we get to answer with these equations. And the acceleration equation we just looked at is kind of one of these, okay? But I'm going to give you what I call the big 3, okay? We're going to have 3 equations. This is the first one. So on your equation sheet, I would get your equation sheet out. Do you know what the prefix kina means? Well, what's the prefix mean? It means motion. Okay, it's motion. So these are our equations for motion. Okay, so here is the first one. VF equals VI plus AT. All right, are those all variables that we know or we're familiar with?
Yeah.
Velocity final, velocity initial, acceleration, and time. Right, those are all all variables that we are familiar with. Now, I want to show you just one thing real quick here, okay? Look at the equation. You don't need to write this part down, but I just want you to see it. The equation we just had for acceleration was VF minus VI over T, okay? If I manipulate this equation, multiply by T, then I would be left with A times T equals VF minus VI. If I add V over to the other side, I would be VI plus AT equals VF. Doesn't that look exactly the same as that one? Yeah. Those 2 equations do the same thing. We will use this version of the equation more often, just because I like the way it's written, okay? So we introduced acceleration talking about the change in velocity right here. And then we kind of move the equation around, and this is considered one of our kinematics, okay? So this is one of our first equations that we're talking about for kinematics. All right, these equations are only constant when we've got a constant acceleration. So that means we are speeding up at a constant rate, all right? If we've got situations in which our vehicle or our object speeds up, then it slows down, then it stands still, then it goes slow, whatever, we have to do those in separate equations. We cannot plug all of that information into one. We have to do them in separate sections. So we have to evaluate our motion in intervals of what's happening at one time. Does that kind of make sense? We cannot do all of it in one single equation. Okay? All right, so this is one of our, did we get time to put this on our equation sheet? Did you guys get that on your equation sheet? Okay, good. That's number 1. And I might even put a little number 1 by it. Because sometimes I'll talk about we need the first equation or we need the second. This is the one I refer to as the first. Okay, so that's our first kinematics equation. Let's try a couple practice with this equation in particular, okay? It says a bus is traveling 30 kilometers per hour. It speeds up at a constant rate of 3.5 meters per second squared. What velocity is it at 6.8 seconds later? So we've got to start identifying our variables here. Before we do a whole lot, I want to identify our variables. So tell me, what is this 30 kilometers per hour? Okay, it is a velocity. What type? Is it initial or final? Initial. So my initial is 30 kilometers per hour. Do we see something right away that we're going to have to do? We're going to have to convert. Okay, so let's go ahead and just do that now. We're going to have to convert to meters per second. So we can divide by 3.6 to do that. And that gives me about 8.33 meters per second. Okay, so I've got initial velocity. It tells me it speeds up at a constant rate of 3.5 meters per second squared. What variable does that go with? Is that velocity final? Is that acceleration, or is it time? It is acceleration. Acceleration is 3.5 meters per second squared, right? So it's saying that for every second that goes by, we are now moving 3.5 meters per second faster. So let's just stop what we're doing for just a second and think. If I'm traveling 8.3 and 1 second goes by, that means now my new speed is 11.8, right? And if another second that went by, it would be 15.3, right? Or whatever. So we got to think about that as we're going. But right now we're just going to keep working, okay? It asks me, what velocity is it at? So that means I'm trying to solve for my final velocity. That's my question mark. I'm trying to solve for my final velocity, and it says at a time of 6.8 seconds later. Okay, do we feel okay picking out those variables from the equation? From the problem? That's a lot of what we do. We've got to be able to identify our variables from our word problem. All right, so I'm going to say that final velocity is my question mark. So I'm going to just keep it as VF equals VI plus A times T. All right, so I'm going to go 3.5 times 6.8 plus 8.33. And that means my final velocity is 32.13 meters per second. Okay, so this one needs to go on our equation sheet as well. This is our second kinematics equation. X final equals X initial plus VIT times 1/2 AT squared. All right. I want to clarify just a couple things about this equation. In the equation, it is only the t that is being squared. It's not the whole term. It's just the t value. Just the time is being squared. Okay? So if you need to put parentheses, you can, but I won't really usually write it with parentheses. We just need to know that only the t is being squared there. Second thing I want to point out, what are these variables? What do they refer to? Velocity, time, they are displacement. So they are how far we've traveled. So both of these are typically measured in meters, right? These are displacement. Okay, they are displacement. And so they're typically measured in meters. We've got to have consistency in our units throughout our whole problem, right? So if my acceleration is meters per second squared, that means my displacement must be meters, okay? Second thing I wanted to talk about is this xi, my initial displacement, is usually going to be 0. Usually I don't talk about a starting point and an ending point. I just say it traveled 40 meters, right? And so my final displacement would be 40. My initial would be 0. So most of the time we just get to leave that out of the equation, okay? But I sometimes I write it as we get started, but for the most part, that xi is going to be 0 since it's our starting location. Okay, so let's try one here. A train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in this time? So we've got a lot of information we've got to start breaking down, okay? Well, okay, yes, but what does that mean?
Well, that was the final velocity.
Nope.
Well, the square.
What does meters per second squared tell us?
The final.
The final, nope. What's the unit? Meters per second squared. What does it represent? Acceleration. So my acceleration is 3.15. What does this tell us here when it says it accelerates from rest? Okay, it was stopped. So what variable does that represent?
Velocity.
Initial velocity is 0. It starts from rest, and now it accelerates at 3.15 meters per second squared. So after 1 second, it's 3.15. After 2 seconds, it's 6.3. After 3 seconds, it's whatever. But we're going to keep calculating that, okay? 1.57 minutes. Does that time seem like it's in the appropriate unit? Nope, because my acceleration was seconds squared. So I need to convert minutes to seconds. And so if I'm going to convert minutes to seconds, I know 1 minute is equal to 60 seconds. And so I take 1.57 times 60, and I get 94.2 seconds. Okay, now what is my question asking me? How far does it travel? So what variable does that mean that we are solving for?
Displacement.
Good. And is it displacement initial or displacement final?
Final.
X final is going to be what we solve for. What do I know about X initial? It's 0, right? It's my starting point. I'm only concerned about what is happening during this 1.57 minutes. I don't care what happened before that. I just want to know what's happening now. Our equation, right? My equation is X final equals X initial plus VI times T plus 1/2 AT squared. But we're going to be able to simplify this equation quite a bit. Okay, so if I start plugging in variables here, I'm going to give myself a little more room. If I start plugging in variables, my X final is what I'm solving for, so I'm going to keep that listed as X final. My XI, my initial displacement is 0, so that's just going to be a 0. VI, what's my initial velocity? 0. And what's anything times 0? 0, right? So I can put my time in there, but do I need to? Because it's still just going to be 0, okay? Then we're going to go plus 1/2 times A times T squared. Okay, so essentially I'm going to drop these two sections of my equation and say X final equals 1/2 times A times T squared. Okay, so let's go ahead and plug that into our calculator. 94.2 squared times 3.15 times 0.5, and that gives me an X final of a lot of meters. I'm just going to round it to a whole number here.
For the 1/2, do you write it as a fraction?
I write it out as 1/2, but in my calculator I do 0.5. This is our third and final kind of kinematics equation here. Okay, so I would call this one our third, right? So maybe label it with a 3 on your equation sheet. This is VF squared equals VI squared plus 2A times our change in displacement.
Oh, that's a square.
VF squared equals VI squared plus 2A delta X. If you prefer to go ahead and write out X final minus X initial, you can do that instead of the delta. If it makes more sense to you to just write it out instead of putting delta X, that's fine too, whatever you prefer. Okay, especially knowing what we know about xi, right? It's typically 0, so you're going to be able to drop that out of a lot of equations. So it's really your choice as to how you want to write that. Okay. Let's go ahead and try a problem with this equation here. Okay, a car starts at rest and speeds up at a rate of 3.5 meters per second squared when the traffic light turns green. How far will it have gone when it is traveling 25 meters per second? Okay, so let's start breaking down these variables a little bit. It tells me it starts at rest. What's that give me? Initial velocity. Yep, VI would be 0. 3.5 meters per second squared. That has to be acceleration, right? We know just from the units alone, it has to be acceleration, right? Because meters per second squared is our unit for acceleration. How far will it have gone? So what variable does that mean I'm solving for? X final is my question mark, right? My final displacement. And it says, by the time it reaches a point of traveling 25 meters per second. So that has to be my velocity final. Oops. Right? Because my unit is meters per second, so it has to be velocity. So what do I know about my initial displacement, or xi? Right? About 95% of the time, xi is going to be 0. It's going to be rare for us that xi is not 0. Okay? So let's go ahead and start looking. Why can't I use my second kinematics equation to solve for this? If I'm trying to solve for x final, why can't I use my second equation? Look at your kinematics equations that you have. Why can't I use the second one? I don't have time. That's exactly right. I don't have time. So I have to use this one. Okay? And this third one says VF squared equals VI squared plus 2A x final minus x initial. Okay? That's what this equation says that we need to use. So let's go ahead and start plugging them in. My final velocity is 25. It's going to have to be squared equals my initial velocity needs to be squared plus 2 times A times delta x, or x final minus x initial. Now, if x initial is 0, do I need to plug it into the equation?
No.
No, right? I could write minus 0, but that's not changing anything. So I just leave it off. All right, and so let's start doing the math. Okay, I'm going to go ahead and start on the left side, 25 squared. That equals 625. My 0 squared, do I need to rewrite that again as 0? Nope, I just leave it out, right? Because if it's 0, I can leave it out. 2 times 3.5 is 7 times x final, right? This whole term is all multiplied together. 2 times A times x final. So now if I want to get x final by itself, what do I need to do? Divide by 7, divide by 7. So that means x final, I got x final to be 89.3 meters.
How would you type them? Oh, you divided it. Okay.
Okay, do we see any problems here? We don't have acceleration and we don't have time. Okay, so this one was a little trickier than I remembered it being, honestly. This one we're going to have to do it in 2 separate equations. So we'll work this one a little bit more together. We have to have acceleration for every single one of our kinematics equations. 0. Okay, we have to have acceleration in all of our kinematics equations. That's non-negotiable, right? Acceleration is a non-negotiable. So we have to find that before we can find time. But we only have one equation that has acceleration but not time, Which one is it? I've got to solve acceleration without having the time. Which one? The third. Okay, so let's do that one first. I'm going to solve using VF squared equals VI squared plus 2A delta X. Right? My final velocity is 25. My initial velocity is 15. 2A times 125. Right? This one is a little trickier because we had two variables missing. So we've got to figure out which one needs to be solved for first and do that. Then we can go solve for the second one. So that one was a little trickier than I anticipated, so I apologize. I forgot I put that one in there that soon, but that's how it goes. Okay, so let's go ahead and solve the math. This would be 625. 15 squared is 225 plus 250 times A. So to get A by itself, I'll subtract over 225. That gives me 400 equals 250 times A. And so that gives me an acceleration equal to 1.6 meters per second squared.
So you would divide 250.
Yes, I need A by itself. So now once I have that information, once I have acceleration, and I've got both velocities, and I've got my displacement, I could really use any of my equations, either the first or the second, to help me solve for time. But which is the simpler equation? The first, right, by far. So I'm going to go ahead and just use the first equation to help me solve for time. Right? My final velocity is 25. My initial velocity is 15. My acceleration is 1.6. And I'm solving for time. And so that gives me a time equal to 6.25 seconds.